Yeah, sorry about the delay here. I think now the mic is working and everything is fine. Okay. So this is lecture number 2. So first lecture was like a huge, it's a sine wave where half the class was about just the logistics and so on. In the second half of the class, we were talking about, mostly we were reviewing classification, and then we talked about backpropagation. Okay, those were the two concepts from last time. Today, we will actually get into some amount of deep learning, and we'll introduce feed-forward neural networks and then convolution neural networks. Okay. So there is going to be some ramp up, but the hope is that you guys interrupt. I mean, obviously, if it's very obvious, you'll fall asleep. But if not, like, interrupt me so that it's clear what the different components of these networks are. Okay, because and you'll see that as we go from next lecture onwards, it's going to be easier because you'll see some canonical architectures today, so that's going to help you understand the other architectures. So with that, let me also briefly mention that we have assignment 1 due next week, and it's mostly, I don't think there is any CNNs there. It's mostly simple networks that we'll see today, and some amount of, there's a simple question backdrop, and also about gradient descent and so on. Okay, so just keep that in mind. So before assignment 1 is due, you should definitely form groups if you have not yet formed groups, so that everything is works out smoothly in terms of grading and everything. Now, so what's the objective for today? Is kind of last time where we left off. It's actually a nice ending, because towards the end we showed that logistic regression doesn't really work for even simple two-dimensional data. Okay, so actually for that data, KNN is really good. I mean, you can just do k-nearest neighbors and it's gonna do well, because it can produce nonlinear addition boundaries. So, but we'll see today that by adding some nonlinearity in our model definition, we can also achieve something good. Okay, so today's objective is really talking about how to make the model beyond linear, because last time logistic regression, or any of these models that you've been seeing, SVM, not any, but like a couple of these models, they're all linear, and we'll add nonlinearities. So we'll make the model more expressive by adding nonlinearities. Okay, expressive just means more complex. Expressive just means they can follow data patterns which are just more complex. So you can have squiggly functions, for example, instead of a linear line, okay, or a hyperplane. So in addition to that, we look at a new architecture in the second half mostly, which is called a convolutional neural network. We'll see what convolution means briefly, and these neural networks, and not just this, but many of the neural networks that we'll see today, in this course, they all have a nice Lego type of analogy, because you can think of layers or blocks with which you can build networks. Okay, so it's really the blocks, understanding the blocks, and at least the motivation, empirical reasoning, and so on is what we want to get to in every lecture session. So what are the specific goals? So we will skip goal 1, which is get acquainted with the basics of Python. It's assumed that you know some level of Python from one of your previous courses. If you're really learning Python for the first time here, that's fine. You just need to put in extra work, because although the code that we write is not complex, but it does, if it's the first time you're seeing it without familiarity with Python or R, then you will have some challenges. Okay, but so we're not going to cover that Python basics today. So directly we'll talk about nonlinearities. So really understanding the notion of nonlinearities, and then some specific vocabulary that is introduced to discuss neural networks. Okay, this is really, the vocabulary is not very magical or anything. They're just very plain, simple explanations of some of these function definitions. So we'll see some of these words. Okay, here I'm saying hidden layer, and we'll talk about what a hidden layer is. The next goal is to understand what a convolution layer is, because we'll look at a neural network called convolutional neural network. And when we define that, and when they define this layer, just think of layer as a subcomponent of this network or subcomponent of this system or model. And there's going to be some names assigned to some operations. So there's going to be a name called filter, and we'll see how that filter works. There's a new name, a relatively new name. We're going to start using tensors as a word. Torch, PyTorch natively has a tensor as an object data type, very similar to NumPy having a NumPy ND array as a data type. So we'll see what a tensor is, and it'll be very smooth because we have introduced the notion of an image. What is an image? It's a three-dimensional array, right? Last time we talked about, okay, there's going to be a red channel with intensities of red colors, green channel with intensities of green colors, and so on. So there's going to be, it's a tensor basically with 3 dimensions. Okay, so it's going to be pretty seamless when we talk about it. And then some minor details which wrap up the definition of a convolutional neural network. One of them is called pooling. Its objective is to kind of reduce the number of numbers we need to compute. Okay, and we'll see that when we get there. Okay, so that's the goal. Really, I do have a PyTorch basics link here, but let me cover the core material and then we can talk about that. And as I said, at any given point of time, interrupt, because if you've already seen neural networks, that's fine. But if you've seen 575, 570, I don't know, 572 and others, if you just see a vocabulary mismatch or something that I'm not covering, then just point that out. One thing we did cover briefly last time, which is the notion of cross-validation. You'll see that much of deep learning models, there's very little cross-validation done. That's because it's very expensive to train even a single, one model, one run with one pass on data is very, not one pass on data, but like for one set of configuration, it's very hard to kind of get the model to train. It takes, at least in real world situations, it may take hours or days. And so folks don't really do cross-validation even to suggest the out of sample to get a proxy for the out of sample error, or to even choose hyperparameters. There's ways to do it, but it's not a predominantly most important thing that you would do. Okay, so with that, let me. So what we'll do today, by half of this lecture, I want to get to a script very similar to the script that we saw last time for the logistic regression example, and just have that script hopefully has a better neural network there, or better model there, and hopefully fits that 2-dimensional data. Okay, that's what we want to get to the first half. See, does this do hello? Is present as a slideshow? This no, actually this is fine. I think the top bar is fine, right? Having a top bar. Okay. Okay, so in the slide deck there is Python walkthrough, but we will skip that section. How many of you are new to Python? Okay. Yeah, this is an elective course. If you you took this, so hopefully you have done Python in some core courses. If not, it's fine too, but then you'll have to kind of get more acquainted with Python. It's always good to kind of double down on a language, and Python and R or any of these languages are kind of high level enough that the more expertise you gain there, especially with some of these packages like NumPy, and so before this course it would be NumPy, Pandas, and so on. And maybe in this course, something like PyTorch or TensorFlow, one of these packages. Then you'll really do well. So let me skip Python. I do want to make a couple of quick comments. One is that the need for compute in this course, right? So I think in assignment 1, you might not need much compute. In assignment 2 and 3, you will need some compute resources. And for your project, you may have ambitious ideas, and you may need a lot of compute. Currently, Google Colab is a suggestion from my end in terms of usage. But obviously, Google Colab has limitations on how much of compute resources you can get in terms of GPU, or sometimes not even a GPU. They do have paid versions which can bump you up in terms of priority or like access to better GPUs if you want it. That's a very seamless way if you really like that Jupyter type of an environment of scripting. The other way is to really fork some budget and get a machine only when you need it. Okay, so if you rent a machine online from a cloud vendor, it does cost some money, like I don't know, $3 per hour, which is pretty high if you continuously run it for months, 4 months or something. But for a day or for just 6 hours of work, it's okay. It's probably acceptable, especially if you want to have like a more uninterrupted experience, and maybe a long running job. Because I've seen sometimes people try to keep the cursor moving or something to keep the collab thing running. So yeah, you could invest in it, and it's just a question of whether you're seeing the next. So the deep learning is going to be there for at least the next decade at the minimum. So it's a question of whether you want to be an expert in that, and if so, then the money you use to kind of fund initial experiments is it's going to be minuscule. Okay. So with that comment about Python, so I just mentioned that because if you have a machine that you run yourself, then you can use your IDEs and stuff like that. I don't know if you can use IDEs with Jupyter, with Colab. But if you don't use an IDE, you should at least learn how to debug. Okay. Obviously, one of the first ways we learn to debug in Python is print, right? So print statements everywhere. So you could also add logging. So logging is very similar to printing, but it'll give you, logging is actually the name of the package which is available in the Python standard library. So you can just, it's very similar to printing. It'll give you a timestamp and whatever statement you want to make. So that way you can also track. But beyond that, there is the PDB package, Python debugger. How many of you have heard of PDB? PDB. Okay. So there's a PDB package, and debugging is a big thing because you will hit errors in maybe not in assignment 1, but assignment 2 and 3. So PDB is a very good, if you want to invest 30 minutes and learn about one module, PDB would be it, because you can know when to stop, when to stop your execution of the program and look at what variables are, what shape they are, and so on. Okay. Obviously, I'm talking about PDB only because if you're going to do it with Colab, I don't think Colab has also ways to probably do breakpoints and things like that, perhaps. But if not, you can just use PDB and it'll give you the same experience. Okay. So anyway, that was my quick, comment about debugging is an important thing if you want to use Colab. If you use an IDE under your own machine, then if you have a GPU-based machine or something, then yeah, your IDE will support how to debug. Like you can click and say, okay, stop at this point or something. Okay, so with those logistical details out about compute, let's talk about the next, an enhancement of logical regression model. Okay, so the first line is basically the model that we were talking about last time when we did the review of classification. Okay, so that's a linear model. From the calculus perspective, if you want to say, it's a polynomial of degree 1 in X, and so that's why it's a linear model. If you want to come from a linear algebraic perspective, then it's not really linear because there's a plus b here. So that makes it not technically linear. It's an affine, function, but but everybody agrees that that's a linear model, right? So now the question is, how do we kind of increase the complexity of this model so that features can now interact with each other and take into account nonlinearities in the data. Okay. So a natural extension from this linear model is somehow we need to introduce nonlinearities. And the way we introduce nonlinearities leads to a network type, a network family called feed-forward neural network. Okay. Feed-forward just means that, there's some operations happening in a sequence. Okay. So it's just a very, simple naming convention here. So this family is a natural extension of trying to make this guy nonlinear. Okay, by introducing nonlinearities, and we'll see that, and also maybe introducing more parameters. Okay, so here's an example. Okay, we'll start an example first approach. So here is an example of a feed-forward neural network. Okay, so f of x has now two sets of parameters instead of one. So w1 b1 and w2 b2. And what is the operation happening? Right? What's the operation happening? It's happening in sequence in two steps. First, x is x is the input. Given x, I'm first computing w1 x plus b1. That's exactly the same as this operation. So I'm doing that linear step first. That's step 1. And then I'm applying a operation here. Ignore this W and B2 parts, W2 and B2 parts. I'm applying an operation which is max of 0, comma, whatever that vector was. Okay. Let's say the vector W1 x plus B1, let's say it's called Z. So max of 0, comma, Z, that's the operation. And that operation, you'll see in the next few slides, is called a nonlinear operation. And we'll see in graphical terms why it is nonlinear. And then that operation, so what is the output of that operation? It's a nonlinear operation, that's fine, conceptually. That output of that operation is still a vector. Okay, it's going to be a vector, and we'll see that in the next slide. Now we have a vector. So that vector, again, I'm multiplying with another matrix W2, and I'm adding a vector B2. Okay, so I have some intermediate vector through the nonlinear operation, and then I'm again applying a linear pair. Okay, which is give me a vector, multiply with the matrix, add a vector. Okay, that's all. So I'm doing two of those linear operations, but in between there is a nonlinearity, which is max of 0, comma x. Okay, so this is called a two-layer feed-forward neural network. Okay, and we'll say why it's called layer in the next couple of slides. Okay, so there's going to be, in the next few minutes, there's going to be some terminology that will be simultaneously introduced through this example approach, but I'll explain them, and if I miss them, raise your hand and let me know or point things out. Now here, there's some accounting of dimensions, but I think it's also maybe off. So let's not worry about this dimension aspects, okay? Because we'll come back to that, the same model in a couple of slides. Okay, we'll come back to the model level. Now let's just focus on this nonlinearity. Max of 0, comma x is an example nonlinearity, and this is what we are calling a nonlinearity. Nonlinearity is just a short form for saying nonlinear function. We're dropping the function part and just calling it a nonlinearity. And so here are a huge list of nonlinearities that was in some right up here. And it also says which year explicitly introduced the neural network modeling. Okay, it's not that these functions were not known before. They were obviously simple functions that people must have written it many times. They were explicitly used in neural network modeling kind of recently. Actually, maybe they've also used before, but so here's a list of nonlinear functions. They're all functions of a scalar input. Okay, scalar just means one-dimensional input, and they're producing a one-dimensional output y. So x and y. And so we can plot them, and we'll plot these three in the next couple of slides. Okay, so these three, because they are some of the more popular nonlinearities in this literature. Sigmoid nonlinearity, which you have already probably seen when you're looking at logistic function, right? 1 by 1 plus e to the power minus x. And then tan hyperbolic or tanh nonlinearity. And the last one is RELU, just stands for rectified linear unit. Some inspiration from electrical engineering. Any electrical engineering person in the room? Okay, do you recognize rectified linear, or rectification process? No. Okay. Yeah. So anyway, there are some historical reasoning in signal processing for some of these choices. Okay, but these are the three nonlinearities that we'll look at, and also, reason about why are we introducing nonlinearity? I mean, in the sense, what is it doing, right? So let's start with sigmoid. Let's understand these functions first, and then relate it back to this two-step thing with the nonlinearity in between the feed-forward network, right? So here's sigmoid. I think most of you probably have seen it before. 1 by 1 plus e to the power minus x. Okay. So basically at 0, x is 0. Then it's 1 by 1 plus 1. Okay. Therefore 1 by 2, which is 0.5. So at 0, it's 0.5. And when x is really large, then e to the power minus x is a really small quantity. So it's 1 divided by 1 essentially. And so it's 1 kind of on the right side. And then here, when x is really negative, then e to the power minus x is like a huge number. So 1 divided by a really large number is 0. Okay. So, and it's nicely, smoothly interpolating between those two ends. In fact, last week's backpropagation example, we had a function like this, and this function is clearly continuous and differentiable, and so that's why we could find the local gradient last time. Okay, so that's the sigmoid. It's a function whose range just means the output only varies between 0 to 1. Okay. So no matter its input, its input can be negative numbers, positive numbers, all over the place, but the output is bounded. Okay, it's between 0 to 1, which is a very nice property. Okay. There's the same picture on the right side here. And I guess this is from probably like a snapshot from last week's backpropagation example. So this is a nonlinearity because if I slightly change input at -2 versus I slightly change input at 6, the rate of change of the function is different. Okay. I mean, it's not. It's if it's a linear function, the rate of change should be something. It should be the same. How much the output is changing as a perturb input should be the same. Okay. So it is clearly a nonlinearity. This nonlinearity makes the overall function, the two-step function, more complex or more richer in terms of capturing patterns in the data. Okay. We'll see that fuller function expression in a second. But what are some challenges of having something like this? Because the moment we said we're going to define a function with one of the operations being a sigmoid operation, then it's going to be a node in some computation graph, right? So it's going to be, there's going to be weights, there's going to be an input, and they'll get multiplied, added together when there's a W, B part. But there's also going to be nonlinearity part, and that's where a node like this will be appearing. For example, let's say there's a vector of length 10 in between, then there'll be 10 such operations happening on each coordinate. And so what is the advantage or disadvantage of having something like this? Okay, just in terms of gradients, let's look at it from the perspective of gradients. Is we know that there's going to be some incoming gradient. If there's a computational node like this, we know that there's going to be some local partial derivative that we're going to compute. This one, and then we'll multiply with the incoming gradient and send it back. Okay, that's just a backdrop mechanical process that we're going to do. The interesting thing about this nonlinearity is obviously that the local rate of change is going to be different depending on what the input value is. Okay, and that's going to influence how gradients backpropagate. Okay, when the input is, for example, -4 and below, and 4 and above, the local partial derivative is actually 0, okay, in the sense of how much is the function changing as I move around here? It's not changing at all, which means that f new minus f old is going to be 0, right? The difference is going to be 0, almost 0. It's not 0 exactly, but same thing here, right? So if you're not convinced with this range, think of 100 and -100. Around those values, if you change the input a little bit, the output doesn't change at all, almost. Okay, so this term basically becomes 0. Okay, that means that when the inputs to this node are kind of large, either on the positive side or negative side, the incoming gradient, doesn't matter whatever the value it is, outgoing, the gradient that's being sent back is going to be 0. So there's not going to be any gradient update if you think about it. Okay, so that's a phenomenon called saturation. Okay, that's a phenomenon called saturation. But if you're in, if all the numbers are nice and they're between, let's say, -4 to 4, then clearly there's a nonlinear, influence on the outputs. Okay, so if the input is at some location, there's some output, but if some other location, some other output, which is not just a linear transformation of the previous value. Okay, and also, second thing is this function is not zero-centered, right? So, but that's a kind of easy thing to fix. You can just subtract 0.5 from everything, then you can say it's zero-centered in the sense that zero-centered just means at some symmetric location its value is 0, and at some before that location maybe it's negative values, and some location positive values. It's good to have that, because otherwise, once you have this node, all the numbers going forward are probably going to be positive. Okay, is that something that you want? Like all the numbers going to the next computation node, so all of them to be positive? It's unclear whether it's desirable or not, but that's zero-centering is another aspect that's unique to this. Unique in the sense that it's one of its properties. Yeah, it's not really unique. But... So that's just explaining this function. Okay, I want to explain the other two functions and then talk about back to the feed-forward neural network. Okay, just so that we kind of ground ourselves into what are these nonlinearities. The second one, it's called tan hyperbolic function. is just a well-known function in calculus, and the function, I think this figure is from Wikipedia. So the function is actually this dashed blue line, or the dashed black line, however you want to see it, but not the dark color. Okay, so it's really this dashed thing, which looks exactly like the sigmoid function. Okay, except the function is value is 0 when the input is 0, and otherwise it's kind of very similar. Okay. So it's the same issue. Gradients vanish. So gradients vanish in saturation. These phrases kind of mean the same observed effect. Okay. So we'll see this nonlinearity later on 3-4 lectures from now in something called LSTMs, or recurrent neural networks. But for now, this is what it is. So just wanted to show that those two are very similar, so I didn't want to spend too much time there. The last one, now coming back to our feed-forward neural network, the nonlinearity. It's called ReLU nonlinearity. It was also used in that 2012 paper, 2012 work, which did that huge bump on ImageNet large-scale visual recognition challenge called AlexNet. So that function is actually this blue function here. Okay, it's a piecewise constant function. That's what people call it. So piecewise constant below 0. It's a function whose partial derivative is 0. Okay, or the gradient is 0. Okay, because the function doesn't change irrespective of what the input is, and when the input is positive, then the function changes exactly to slope 1. Okay, the partial derivative is 1. So it's a really nice function where you even know, it doesn't depend on the input in the sense that it only depends on the sign of the input, what the local gradient is, and doesn't depend on the actual value of the input. Okay. So here you can see that some other function is approximating it, but don't worry about the green function. So that's why it's called a rectifier. Okay. It's basically rectifying in the sense that if you think of a line passing through 0, it would go negative. Rectifier just means like it's pushing it back to the positive side. Okay. So why are we looking at this function and these previous two functions is because empirically they've been found to add they are the canonical choices for defining neural networks. You can always define a neural network with any other nonlinearity that you can think of. X squared, for example, is a nonlinear function, right, of x, quadratic function, right? You can use it if you want to, but these are the canonical ones that people have preferred for various reasons, and they perform well. Okay, one of the reasons, at least on the empirical side. Now, one of the issues with even this one is that if the numbers are always all negative, then also the local gradient is 0, and then you don't pass back any information back to the previous node, and therefore you may not get a gradient update at all, reasonable gradient update at all. Okay. So which has some implications on if you have some, you start from some W0, B0, or W0, B0, sorry. The parameter values, if you initialize to be some, like let's say all of them are negative, then it's an issue, right? All of them are negative and your inputs are, let's say, small enough that a negative matrix times an all entry negative matrix times that input happens to kind of ensure that all the numbers are negative, then you won't have any gradients flowing back, and then you will not be moving from that initial value, for example. Okay, if you do the gradient update. So I mean that's what we just mean by permanently dead reduce, in the sense that they're getting inputs as negative values, so they're not getting returning back any gradient. So there's not going to be any gradient update in your gradient descent procedure. Okay. So okay, that was just the understanding what are nonlinear functions here, one-dimensional functions, simple to visualize. But let's come back to the feed-forward neural network architecture again. These functions, they operate at per coordinate level. Okay, so in the function expression, it was not clear. I just wrote max of 0, a vector. That expression, and it's also written at the bottom, that expression just means I'm operating this max of 0, input at every coordinate. Okay, so every coordinate, I'm just checking whether it's, for example, greater than 0 or not. Okay, if it's less than 0, I'm just setting to bit 0. If it's greater than 0, I'm just whatever, it's going to be that number. Okay, that's what the function is. right? Now, why that nonlinearity, right? So if that nonlinearity was not there, right? If that nonlinearity was not there, just it's not written on the slide, but if the nonlinearity was not there, then you can think of what's happening, right? It's W2 times W1 times X, right? Plus W2 times B1 plus B2, right? That's, I'm just dropping the max of 0, comma whatever. If you drop it, then it looks as if it's W2 times W1 times X, which is like some new matrix times X plus some constant vector, okay? So if you drop the nonlinearity, it goes back to your linear function, okay? I mean, it's not quite right, but in terms of like informally saying, it does kind of go back to your linear function, okay? So you do need that nonlinearity to get away from the linear function family, okay, at least on paper. So that's one of the kind of necessities. And these nonlinearities are basically making your function, this function, capture richer patterns, okay? And we'll see that in an example demo code that we have. Yeah. Yeah. But any questions here? Yeah.
Can I explain this part once again? I don't understand like how the nonlinearity done it.
Oh, if you drop the max of 0, so if you drop the nonlinear function, then you just have W2 times W1 plus X. Sorry, W2 times W1 X.
Okay.
Plus W2 times B1 plus B2. The second part is not related to X, so it's just some vector. And the first part is W2 times W1 times X. Okay. I'm not saying that, so it is linear in X, but if you're going to do gradient descent on W's, then there is some nuance that I'm skipping over. Okay. But nonetheless, if you think of a function of X, yeah, it is a linear function of X. Okay.
And the W's will also be matrix, right?
W's are matrices, yes. W1 and W2 are matrices. Just like the last time W1 was a matrix. Yeah, W2 and W1 are matrices, and B1 and B2 are vectors. So this is a functional form. And now why stop at like, W1 and W2? Why not introduce W3, B3, or W4, B4, or maybe W10 and B10? Yes, you can. And that's exactly what a feed-forward neural network is, where your building blocks are these linear steps, Wx plus B. Okay, so think of if you want to think in terms of computation graph, think of a big circle which does Wx plus B, and then a small circle that does max of 0, comma whatever its input is. And then again a Wx plus B, and then again a max of 0, comma X, again a Wx plus B. So you can just arrange those nodes one after the other, and you don't have to stop at two steps like this, right? So that network, if you have a lot of such steps, is basically a deep network, deep feed-forward neural network, okay? So you don't have to stop there. I mean, it's just an illustration for illustrating the feed-forward neural network, okay? And why would you want to do that? Because of this nonlinearity, there is a kind of way that the input features are getting mixed up quite a bit from stage to stage. Okay, this is linear transformation. There is obviously the output. If it was just a linear function, okay, just a linear function Wx plus B, then think of each individual coordinate of X, right? So it gets multiplied with some weights to produce the first class label. So think of first class label or the first core is just a weighted version of coordinates of the input. Okay, remember the first core S1, for example, is just the first row of W times X. Okay, second score is the second row of W times X. Okay, that's just a matrix. If you have to visualize in terms of a matrix, okay, matrix and a vector, the first score is just some linear combination of x's. If you introduce nonlinearity, and now the x's kind of so some combination of x's and some other combination of x's also get now added together, but now they're what do you say? I don't want to kind of get into too much of the function like visualization, but the nonlinearity kind of mixes that. Now you have like quadratic functions like x1 times x2, and things like that happening. Okay, we'll see that actually. I want to show a UI, and we'll see that in a second. But I want to first at least talk about the nomenclature, as in some terminology that is new okay, in this slide. First of all, feed forward, we just said it's just this sequence of linear transformations is what makes it feed forward. There's a pictorial representation which looks like a computational graph, but it's just an informal diagram. What it's supposed to show, this picture is supposed to kind of represent this function, where these black arrows represent one of these Wx plus b pairs. Okay, so this is just, it's not exactly a computation graph. You could potentially make it into an exact computation graph, but this is just for illustration, and you'll have similar illustrations for many of the neural networks that we'll see in this in this course. Okay, so these circles just represent those vectors. So there's an input vector, there's an intermediate vector after one of the Wx plus b operations. In fact, this vector also subsumes that max of 0, x, for example, or any nonlinearity, that those steps, and then one more Wx plus b, W1 times input z, let's say it's called W times whatever its input is, plus b, and then some output numbers. Okay? So just think of the circles as like some vectors, either input or intermediate or output, and then the arrows kind of represent that that stage of doing a Wx plus b operation. And the circles also, at least the circles in the center, you can just think of subsuming or just considering the nonlinear operation there as well, because nonlinear operations are per number. So you can also think of, okay, maybe my input is 3-dimensional, my intermediate vector is 4-dimensional, and my output is 2-dimensional. If you want, it's still okay to do that. So that's a diagram. You will see that similar diagrams in a second. Because this function has two pairs of W comma B's, we call it a two-layer network. Okay, or two sets of these black arrows. Okay, and in terms of layers, you can call, so there is going to be one of the layers is going to be kind of a degenerate layer. Although we're calling it a two-layer neural network, although I'm talking about three names here, one of the names is kind of irrelevant. So you can talk like an input layer. From here to here is a hidden layer. From these black arrows to the output is the output layer. Okay, so the input layer is kind of redundant. It's not really an input layer; it's just input vector there. So that's the layer terminology that we're ascribing here. Okay? So this is one step or one layer here, including its output, and this is one layer here. Okay. And when the people say layer weights, the weights just mean the parameters of this layer. Each circle here represents a node, also a neuron. Okay? A node, a neuron is the same thing. We'll see in the next couple of slides. Each circle you can think of as like a coordinate of the vector. Okay? So input, it doesn't make sense to call it a neuron, but let's say we did create a 4-dimensional vector in between. Then the 4 coordinates, you can call it 4 neurons or nodes. Okay. Nodes is obvious because it looks like a graph, so maybe these are nodes. Yeah, and we'll call them neurons also. I will see in the next episode. Yeah.
Within this circle, so you are saying that within this circle in input value, you have the different vectors. So those vectors are same as the features of a data set? No. So we'll actually look at one example, but I'm saying each of the circle represents one number. So let's say we have a input which is 3-dimensional. Okay, 3-dimensional means 3 coordinates, right? Three coordinates in a vector. So the input is 3-dimensional, 3 numbers or corresponding to one feature vector. And let's say the first set of black weights, the W matrix there is 4 cross 3. Okay, so that W matrix has 4 rows and 3 columns. That times this 3-dimensional vector will produce a 4-dimensional vector, right? 4 rows and 3 columns multiplied with the 3-row column vector produces 4 numbers. And just think of these as 4 numbers. Okay, and then each number is now also being applied. A nonlinearity is being applied to each number. Okay, so if the number happens to be negative, set it to 0. If the number is positive, leave it as it is. That's what a max of 0, x does. Right? So function defines that arrow.
These arrows just kind of roughly correspond to the W and B pair, the W matrix and the B vector. Illustration. This is just an illustration. Don't worry about this. This is like as definite as it gets, right? This is the function definition, fully expressed in terms of parameters. So don't worry about the illustration if you're not able to map it. But I did say that this W1 and B1 correspond to these black arrows, and W2 and B2 correspond to these black arrows. If you want some like mapping, yeah. relation. Finally, I mean, as I said, like nonlinearities are not shown in the diagram, but nonlinearities are exactly that max of 0, comma some input scalar single valued number. That's a nonlinearity. And when you apply that, the people use the word activations as the outputs of that application. Okay? So when you do W1 x plus V1, that vector, the coordinates of that vector are called pre-activations. And when you apply that function, max of 0, comma whatever that vector, pre-activation vector was, that final vector is called an activation vector. Okay, it's just terminology, and I know it's kind of overloaded that we are introducing so much terminology, but you'll see that it's kind of consistent throughout the course. So first time it may be a delta, but hopefully next few times it will be clearer. But as I said, if you're getting confused with names, this is the function that's being discussed currently as an illustrative two-layer feed-forward network. Yeah.
So the pre-activation was W1x plus V1, right?
Yeah.
And the final activation is W2 max plus V2 or just the
No, just the max. Yeah. So W2 with that activation plus V2 would be output vector. So doesn't have to be that activation is only here. So if there were more steps, every step would have its own activation. Okay, so you can call all these intermediate computations as activations of that layer. Okay, activations after the nonlinearity being applied to that layer. Yeah. Yeah, I mean, so by the way, this is not the only feed-forward neural network. This is the simplest network in the family, right? We can chain it many times. There's so many choices to make, right? Why is it 3 dimensions? Why is it four dimensions here, right? There's some choices to be made. And why this nonlinearity? You can use other nonlinearities. So there's many choices to be made. Yeah, which is what I was going to say here, that roughly number of layers is the same as the number of W, comma B pairs. If you're thinking of this family of neural networks, and the neural part is because nodes are called neurons. And some of the questions you can ask is clearly how many number of layers. Like previous example, illustrated example, there were 2 layers, and even within that, what should the dimensions of matrices be? Because we can obviously fix the dimension of the input and the output because we know how many classes we want to classify or what regression values we want to compute. That's fixed. How many input feature, maybe that's fixed because we don't want to do more feature engineering. But in between, what are the other dimensions of the matrices? We can actually choose a lot of. We can choose a lot there. Okay, the number of rows of W1, for example, we can choose it to be 100. It doesn't influence anything. I mean, we just have to ensure that from that 100-dimensional vector that we produce, we can somehow come back to whatever, like a 3-class or 2-class classification that we're doing. Okay, so there's some choice, degree of freedom there. Yeah, the next slide is so this slide is just talking about backpropagation. So I think there's nothing new here. This slide is just saying that now you have to backprop with all the parameters. So not just the updating W1, B1 to old values to new values. You also have to update W2 and B2 from old values to new values. That's all the message of this slide is. So I will skip that. And now let's actually look at an implementation that's there in the that's there in the examples folder. Okay, so I want to quickly show that. So what we're going to do is run this in the same folder. Last time we ran linear classifier. So this time we're going to run the feed-forward neural network. FFN stands for feed-forward network. Okay, so let's run it and just confirm that, yeah, the nonlinearity is doing something. And we'll do a couple of demos. Okay, not just this, but let me get this. Okay, so I'm just okay, so this is an example that we're going to look at. So but at this time, you should to become familiar with plotting. Plotting related, some choices have been made with matplotlib, but there are other plotting packages. Okay, there are many plotting packages in Python that you can, you should kind of get used to. Obviously, you can always export things and show in Tableau or other places, but you can also use the, matplotlib is one of the packages, but there are others. Okay, so it's the same. Let me just run all. I don't know if I connected, still connecting, but in the meantime, this is the data that we saw last time as well, right? So, so this was the data, right? The swirling data set that we saw last time, where the logic regression model did not work that well. And so what we're doing now is exactly what we wrote in the slides. We are going to create a W and B pair. We're going to have one extra W and B pair, so W2 and B2 here. Okay. On top of that, we're going to choose a number of hidden units or not hidden units, number of neurons, like the W2's number of columns or the W1's number of rows to be 100. Okay, so instead of in the figure there were only 4 circles. Instead of 4 circles, think of 100 circles. Okay, that's a lot. You may say, why 100? Why can't you use 10? There are a lot of choices to be made. Okay. Again, just like last time, this is transpose, so that's why you see the number of columns here to be 100, but in the slides it's a opposite, only because this is transpose, only because we're doing vectorized operation in this code. Okay, vectorized operation just requires transpose, that's why it's transposed here. Okay, any questions here in terms of, yeah?
It is 100 is the 100 hidden.
Yeah, let's just do
of the hidden, like we'll compute it 100 times each of that. Like number of inputs we have.
Yes, not the number of inputs. This
But
is
4 instead of this 4 here.
Yeah, 100. So how did 100 come, right? Because the dimension of W1, right? X is 2-dimension in the picture because there are 2 numbers, X1 and X2, which bring out a point, right? So X is 2 dimensions. W1 has to be, has to have 2 rows, sorry, 2 columns, because the dimension of X is 2. But the number of rows of W1 is kind of something I get to choose, right? So the number of rows kind of corresponding to this figure is 4, but the number of rows in the code is 100. I mean, we can change it to 4 and also run it. Means doesn't change anything. Let me just double check that the D was 2 right here. Yeah, X dot shape 1 will be probably 2. If not, we can just okay, yeah, just 2. So we have that, and then this is the same as before. Logic regression had a regularization parameter, like a L2 norm regularization parameter. We didn't focus on it last time as well. Last time, I think it was very last few minutes of the lecture, so we didn't focus on the code. We'll also not focus on the code today, because this code and the previous code, they are actually showing you explicitly, if you had to do backprop without using any third-party library like TensorFlow or PyTorch, how would you do it? Okay, so it's doable. It's just hard. Okay, and that's why you kind of appreciate, okay, this packages like NumPy, not NumPy, but PyTorch and TensorFlow, they do a lot of things behind the scenes for us. As long as you can define the forward function, as long as we can say, hey, W1, B1 are used to compute something, and that something is used to compute W2 plus B2, and so on. As long as you can describe the forward operation, then behind the scenes gradient descent can happen. Okay, we'll look at it when we get there. And yeah, step size is chosen to be 1, so that might have messed up a lot of things, but let's see. So actually, doesn't look like that. So I see a lower loss value here compared to last time. I think it was 0.78 or something. I mean, I can open it, but so it looks like there's lower loss, but it's not 0. So I mean, we can look at the figure and see why it's not, but why is it not 0? Oh, okay. Yeah, maybe there's some errors happening here. They're too close, perhaps, because at least the moment you're far away from the other colors, you're able to kind of nicely separate out the decision boundaries. So this is what you get with that just one hidden layer. One nonlinearity in between a two-layer neural network. Okay. So that I guess I also mentioned. So it's called a two-layer neural network, but it's also called a one hidden layer neural network. Okay. It's just think of the difference is just when you introduce the word hidden, just subtract by -1. Okay. So you can say 5-layer neural network or 4 hidden layer neural network is the same thing. And you don't have to be too gung-ho about getting this correct. I mean, people are not that interested to know whether you had like a 5-layer network or a 6-layer network. They just want to see, oh, was your function expressive enough that you captured the patterns in the data, and if there was a meaningful change from going from one size model to another size model. Okay, and where size, I'm just meaning like how deep it is. Yeah. Okay, so this is I guess the some improvement from last time. So there's also I think it's there in the lecture slides, but I thought I'll show it to you since we're on the browser page. Is a in-browser execution of of the same idea we've been covering from the last lecture to this lecture. Okay, so let's drop the hidden layers and let's choose the simplest data set, which is clearly separable, right? So this is the data set. Okay, it's two-dimensional, right? X1 and X2. So there's a orange cluster and there's a blue cluster, which means that there's a two-class classification problem, and I have 0 hidden layers, which means that it's just a logic regression model. Okay, and and I also chose simplest data set. There are other two-class data sets which are much more complex, and then you have many names that some of them we have seen. Like last lecture, we saw what is the regularization. So I think this is just that coefficient in front of your L2 norm or something. L2 norm, the weights of the model. We chose it to be classification. It's fine. We did that last time. Regularization. Let's say we chose L2. That is the sum of the squares of the entries of the matrix of your logic regression model. This logic regression model is only two inputs and 2 classes, right? So it's a really small W matrix. Activation, we have seen. Activation doesn't make sense here. There's no hidden layer or no layer actually. And then there's the learning rate. That's the optimization related parameter. Remember the gradient descent, there's an alpha and beta that we saw in the slides. So here it's just one fixed number, which is something. And then, and that's it. And so actually we don't have to train anything, but yeah, at least you saw a little bit of changing of the slope of that decision boundary. Okay, so this is the decision boundary. And so there's a really good, and you can see actually the loss, right? So loss function immediately went to kind of 0, or it was already there. So it really didn't have to decrease. But let's, the more difficult data set, right? So here, obviously we can't find a linear decision boundary. So the loss is saturated at 0.49 or 0.5. Basically, it's just a random coin flip. Okay. But of course, this is logic regression model not working well on this data, two-dimensional data, very similar to the swirling data that we have. And the question is, what can we do, right? I think last time we discussed that, okay, even if you have a linear model, that's fine. We can just make, we can do feature engineering. We can just make all sorts of functions of my input data. And so that's where you can see I can enable, I don't know what function this is, but what is X1, 2? Maybe it's the first, it's the rate of change of the function, maybe. I don't know. Sorry, of the X feature. But anyway, there's like, you can feature engineer. Okay. And maybe in this dimension, I don't know, you obviously have to play. Oh, you don't have to play. So it turns out in this high, you did feature engineering, then you are able to separate the 2 classes. Yeah.
I'm curious what will happen if we use the linear activation function.
Yeah, we are still in the linear function class. We're just changing the data set and adding feature engineering. We'll now say, okay, let's not add feature engineering. Let's not do feature engineering. Let's now make the function more complex and see whether we can learn. Okay.
And one more thing, in the slide of the review activation function,
Yeah.
there was a point written that it has no vanishing gradient descent because everything is negative.
It has no vanishing gradients on the positive side. And obviously the negative side, it just, there's no gradient. It is vanishing. It is
So
vanishing.
we are considering it to be a good thing that we are just neglecting all the negative values.
No, I mean, there are other slight variations of ReLU. I think in your assignment, there is a slightly, I don't know what it's called, but a slight variation of ReLU where there is the slope on the positive side is a 45-degree line. And on the negative side, there is it's not zero, but it's like slightly negative. Okay.
It could be, but
Yeah, there is a different nonlinearity which captures that. Leaky ReLU, I think that's what it's called. Sorry.
okay.
And the name elapsed my mind. But yeah,
And
skip. Yeah.
just in any case, if the weight is also negative, but the input is positive, so
Yeah.
not even consider that.
Yeah, if the input numbers are all positive and the weights, all the weights in that coordinate, for example, the one row of them are all negative, then yeah, then it's the as long as the bias term is like also like not effective, let's say 0, then yeah, you'll get a negative number, and so the gradient will not pass through that. Yeah, in the sense that those weights, might not get changed in the gradient descent update. Yeah, that's true. So I'm still running this. Okay, so now the question is, can we get rid of these features and use nonlinearity, right? So use layers. So this would be a 2-layer neural network or one hidden layer feed-forward neural network. Okay, where if you want to confirm, let's say, I mean, there was 100 in the code. We're not going to add 100 here. I don't know how much is the max. Oh, okay, let's say some 7. And now you can talk about, okay, which nonlinearity should I use? I can use ReLU. Actually, there's a meaning to internal representations here, but I'm just not focusing on that. So let's say, we did not do any feature engineering, and we added some nonlinearities. Added a layer and then added nonlinearities. In fact, if you want, we can add one more and then increase the I have no idea what works. So let's try. I mean, okay. So you still got somehow, I mean, by the way, I was lucky. I didn't think of these parameters, but you still got a nonlinear boundary. You didn't feature engineer there, but you made your function complex. Okay. Yeah. So any questions here for these two? I think you should play around with this to just kind of cement your ideas of obviously linearity versus nonlinear functions, but also just the names, regularization, regularization rate, activation, learning rate, and so on. You just play around because this will give you and you can also play around with choices related to the optimization problem. The batch gradient descent, watch how much is the batch of data that you need to use and stuff like that. But here, I don't know if there's a lot of details on how big is the data, but everything is happening in the browser, so you don't have to install anything and try this out. Or you can do on Collab, you have the scripts, so you can just play around. Yeah.
Okay, how do we know that how many layers we set up and how many layer?
Yes, that's a lot of choices to make, and we don't have a recommendation here. Yeah.
So let's say if you're not working on this and working on our own.
Yeah. Yeah, so these choices influence the model specification, and given a model specification, you made these choices, and you have like a model spec. You train the model, and then you look at obviously in sample and out of sample errors, and the gaps and stuff like that. So it's very similar to what you did with other model classes, right? So it's just a question of whether you're overfitting, if there is any weak signal or some information about overfitting or not. So you have to have a validation set to kind of identify those things. Yeah, but a priori, it's not. There's no like rules of thumb. Yeah, I mean there may be, but I am not aware of. Yeah. Okay. So what time is it actually? Yeah, 7. Okay. That was what we just did. Any other questions about feed-forward neural network? Okay, it's really, it's really, we are introducing nonlinearities, and that's what's making X1 and X2 compose with each other through this, through the through the function. Okay, instead of you explicitly feature engineering first and then doing a linear transformation, those happening inside. Okay, and they're not named that these are x1 times x2 happening, but yeah.
Now, how do we know which nonlinearity to choose for which problem?
Yeah, I mean, you can choose any. I mean, so there is a convention. The ones I highlighted are the ones that are typically shown in canonical models, but in your application, you can choose any, right? So the question is, does the variation in nonlinear choice influence your outcomes heavily? It turns out they don't influence that much. Okay, at least historically, from what I've seen, they don't influence too much. Yeah. So any of those lists. So people once thought that maybe, I mean, by the way, in theoretical terms, any nonlinearity will be fine. Okay, but in practice, some nonlinearities have issues like vanishing gradient problem on both sides instead of ReLUs, which have on one side there are dead ReLUs, so basically numbers, gradient don't get passed. So there are issues with all sorts of things, but ReLUs seem to have ReLUs were the ones used by AlexNet, which got a big improvement, and a lot of people use ReLUs. By the same time, people have been inventing new nonlinearities all the time. Yeah. So let's continue with a little bit more discussion on feed forward. So next few slides are actually not directly jumping into a new network. They're slowly motivating us towards a CNN. Okay, so it's still we're gonna still discuss feed forward networks, but slowly get to CNNs. Okay, but when we get to, we'll take a break in about 15 minutes or so. Okay, 10-15 minutes. So yeah, so now we are switching topics. As I said, we're going to slowly talk about CNNs. And to do that, like what do CNNs do, right? So they are basically going to be very similar to feed-forward neural networks. There's going to be a sequence of computations. It's just that those steps are not WX plus P. That's all. So the step will be looking slightly different. Except for that, everything else, the sequence nature, like in the sense of layers to layers to layers, that's, same idea holds, at least illustratively. Okay. So in feed-forward neural networks, in this family, each neuron, right, each circle, for example, in there's only we only saw one hidden layer neural network. So each neuron is associated with a bunch of weights and a bias. Okay, so you can think of each neuron as being associated with a bunch of weights and a bias. And there's a picture in a slide or two I'll show. What are these weights? Just think of each row of the W matrix, let's say W1, you can think of those weights associated with that neuron. Okay, because remember, because that neuron is just those weights times the input X. So you can think of those weights and the first coordinate of the bias to be associated with that neuron, okay, the first circle. So that interpretation still holds for CNNs. Okay, so we'll see that interpretation again with a picture in the next slide, but that will hold for CNNs. So what I mean, right? So both for CNNs and feed-forward networks, each node or neuron is basically doing a dot product of vectors. So whatever is the X, basically X times W, rows of W are basically the dot products. That's what's happening at every neuron. Okay, and that's true for feed-forward network, and we'll see in the next slide a picture. And then each neuron also applies nonlinearity. Okay, we saw max of 0, whatever the input resultant of this dot product is. Okay, dot product or inner product is the same thing. It's just a element-wise multiplication of coordinates of vectors. Okay. The only difference, and it's a key difference actually, and requires us to spend another hour about it, is because the difference is that the number of parameters is going to be way less. Okay. Now you may say, okay, why do we care about number of parameters at this point? They all seem like big, models compared to linear model, but we'll actually account for this. Okay, why do we care about it, and why the number of parameters is reduced? Okay, so let's come back to the feed-forward network. This is what I was saying in the previous slide. So given a vector, right? If you focus from a single neuron viewpoint, this is from a single neuron viewpoint, this picture is basically saying that given a vector, I will have a bunch of weights associated with that neuron. I'm going to do element-wise multiplication. So x1 times w1j, x2 times w2j. What is the j? J is like saying this is a jth neuron, like the jth coordinate, the jth neuron in that list of neurons or nodes that you have. Okay, so I'm going to do element-wise multiplication and do a summation. The sigma is just saying, okay, pictorially do a summation. And then I'm gonna add yeah, I don't, yeah. Yeah, I'm gonna add, let's say this particularly the bias. I mean, I'm gonna add some extra number, and then I'm gonna apply a nonlinearity, and whatever that the max of 0, x or like sigmoid 1 by 1 plus 0 minus x, whatever, and then whatever is the output is called the activation. So before applying this nonlinearity is the pre-activation. Okay? So this is the viewpoint of that each neuron is associated with a bunch of weights. It just so happens that in feed-forward neural network, every neuron has its own set of weights. Okay, it makes sense. I mean, every neuron has its own W matrix, has its own, every row of the W matrix corresponds to a neuron, which means that every neuron will have its own unique row, and so it has its own weights. Okay, and you'll see that in CNNs in 15 minutes later, every neuron may not have its own set of weights. Okay, so there's going to be a difference. Any question about this picture? Okay, so this picture, I only showed this because there's some very hand-wavy relation to a biological neuron where you have, I guess, signals coming from other neurons, and then some sort of like thresholding or some kind of aggregation of the information, and then maybe some like a threshold operation, not threshold, but like if the signal is high enough, then maybe you propagate that signal to future or the downstream neuron or something like that, real neuron, biological neuron. So, okay, so that was just the neuron level perspective. Let's come back to the layers. So feed forward, we can actually visualize the connections for an arbitrary neuron. So these were the neurons of interest. And input, there's nothing is degenerate, they're just numbers. So we don't have to worry about them. So each of these are neurons, and even these you can say neurons. I mean, although here we don't apply nonlinearity generally, like these are scores, think of them as scores. We do apply nonlinearity to get them to probabilities values, but they're not like activations there. So really everything is happening here because it's such a small network, just a 2-layer network. So here, I mean, for this neuron, we can clearly see that these are the 3 incoming connections. Same thing with this neuron, these are the 3 incoming connections. So every neuron has the same incoming, at least the same incoming vectors. This vector, sorry, three-dimensional vector. Except the weights here and the weights here could be different. So each neuron has its own set of weights. Okay. Now we're going to try to see, okay, let's now talk about a data set where perhaps using a feed-forward neural network is wasteful. Okay. So what is the data set? It's a classification data set. 10 class classification data set, or 10 class classification data set. And here's some sample images. Sample images. So each of this, for example, this one is like an airplane is a label, and this is the input. Okay, this is each one of them is an X, right? The X is 32 cross 32 cross 3. Okay, 32 cross 32. I mean, maybe in MNIST it was 28 cross 28. Here is 32 cross 32. But it also has color here, unlike the MNIST 100 digit data set. Okay, so that's the data set. If you just think of feed-forward networks, right? So if you just then you have to do something, right? You can't pass a tensor, right? X has to be a vector for feed-forward network. So we just vectorize it. Vectorize means, I think last time somebody asked, so it's just put each row one below the other, or each column one below the other, and just aggregate them. So you get a really long vector. So 30 times 30 times 3, right? So it's about 3,000. Yeah.
How was the data set 32 by 32 by 3? I don't understand.
Not the data set. Each image, each X is it's an image. And last time we discussed that an image has a width and a height and a depth. So this image is 32 pixels times 32 pixels times 3 channels, RBG channels, each image. So there, I mean, the CIFAR 10 data set has a lot of images, okay, a lot of data. And in fact, you will work with this data set, not in this assignment, next assignment, and then you'll hit some computational challenges if you do something naively. And so, but yeah, we'll get there. Yeah.
In the last slide, you have mentioned arbitrary. Is it a terminology?
Oh, okay. Arbitrary means pick any generic neuron. Just meant arbitrary just means Yeah, it's nothing terminology related.
Well,
I
it has,
said, pick a generic neuron here. I'm just asking, can you see what connections it has? That's all. Yeah. Yeah, the word arbitrary doesn't mean anything. So it's clear, right? Why it's I mean the each x input is not a feature vector anymore. It's actually a tensor, but you have to vectorize it if you want to use a feed-forward neural network. Okay? Because it's wx plus b, where x cannot be another matrix. If you do a matrix multiplication, you could get a matrix out of it, but that's not what we want. We want a vector out, because b is a vector, right? So if you just vectorize it, so this is about 900, right? So yeah, 900, let's think of it as 1000 opposed to multiplication, and then 3000 numbers. Okay, 3000 numbers, that vector length approximately, right? So each neuron in the feed forward in the first hidden layer, right? So let's say the first hidden layer has 10 neurons. I don't know. So each neuron would have about 3000 numbers associated with it, right? Because the input is 3000 numbers. So obviously the weights have to be 3000 numbers, so that the dot product gives you one number, and you add a bias, do a nonlinearity, right? So there's 3000 numbers associated with one neuron, okay? And if you have 10 neurons, you have 30,000 numbers. If you have 100 neurons, you have 300,000 numbers, okay? So that's a lot of numbers, right? And if you have instead, this is really small, right? But the reality is, let's say your screen size. In fact, this is actually on the lower end. Many of your laptop screens have like 1600 times 1200 or 1900 times 1000 size pixels. Or you think of an iPhone taking iPhone or whatever phone taking pictures. This is like really low resolution. This is actually about a 1 megapixel image, right? It's about 1000 times 1000, so 1 megapixel image. Okay, but that's really low resolution today. Okay, so if you have this many, so if you have 1 megapixel, 1 million number of pixels, then each neuron will have a million weights associated with it. If 10 neurons, you have 10 million numbers. Okay, or 100 means you have 100 million numbers, right? So anyway, too many numbers, right? And that's just up to one hidden layer. Now, if you go to the next hidden layer, maybe if you only choose 100 neurons, then maybe the next one is not too many weights associated with the next set of neurons if you had one more layer. But the first layer has too many. Okay, so you can see that maybe we can do something. We may want to do something there to deal with this explosion in the number of numbers. Okay. And that's the rest of the story, to deal with those number of numbers while still taking advantage of some inherent characteristics of images. Okay. So by the end of, I guess, by the end of this lecture, you'll see what is it that we're taking advantage of. Okay. I don't want to kind of talk about it now, because we're going to first define an architecture where you can see that the parameters is reduced. Previously, we saw that the parameters is like too many per neuron. We're going to first reduce that, and then we can see what is it that we're relying on because that we got this reduction. Okay, so we'll kind of now start thinking about the neural net CNN architecture. The new idea is going to be that layers will have two additional attributes which were not there. Okay, so previously the layers were like wx plus b. W, so each feed-forward layer was just the weight matrix and the bias matrix, and its output was just a vector. So it has one dimension, length of a vector. Okay. Now we're going to define this layer such that the output is going to also have a width and a depth. Okay. So the output is going to be three-dimensional. It's going to be a tensor. Okay. So we're going to change this, adapt this network definition such that now we're going to work with tensors as outputs, tensors as inputs, and tensors as outputs. Okay. In contrast, feed-forward network only had height. Okay. So I'm going to try to relate it to feed-forward network because it's not too different. Still neurons, still weights, dot products, same things happening. It's just that by thinking of these inputs and outputs not as vectors but as tensors, then you can see why there is some reduction in number of parameters. Okay. And the layer width and depth are nothing to do with the number of number of steps in the number of steps in the network itself. Okay, that depth is different. Okay, so how do we do that? So it's just visual. So previously we had this. like a vector to a vector to a vector, right? Now what we're going to do is what we have is actually a image, right? An image is like a slice of bread, actually 3 slices of bread, right? Because we have 3 channels. Like if input was like this, we could either think of vectorizing that input, which is what I was discussing, where I was multiplying the numbers and saying, okay, X is like really long, or you can leave the input as is, but we can start talking about neurons. Okay, neurons not arranged linearly, but like in a square or like basically like again a slice of bread, where each neuron looks at every entry in the input tensor. There's nothing happened from this picture to this picture. It's still the same. Okay, still the thin slices. If you want to, okay, let me step back a bit. If you don't want to think of the Seyfarth image, just think of this, right? This input, this vector leading to this vector leading to this vector. You could always arrange a vector into a matrix, right? If you had 100 numbers, you can just make it into 10 cross 10 matrix. It's just arrangement of numbers. There's nothing else going on. Okay. Let's say this was 100 dimensional, we made it into a 10 cross 10 matrix. And let's say this is 16 numbers, 1 6, and I can make it into a 4 cross 4 matrix. Okay, make it in the sense that just arrangement of numbers. It's still the case that each number out of the 16 numbers there in the 4 cross 4 matrix still kind of uses all the 100 numbers. That's what these green arrows are showing, that each number in the intermediate layer is still kind of working with all the 16 or all the 100 numbers, right? So nothing, I just arranged things which were vectors now became things with width and height. Okay, so no depth yet, but width and height, right? And same thing, output was two numbers. Instead of 2 numbers, I can think in terms of like okay, it's just degenerate dimensions. Okay, here, but okay, let's say it's still 2 numbers. It's look a vector, but it looks blank. I mean, in the sense it's a row vector. So we can view feed-forward networks as having width and height. That's not a big deal, is what I'm trying to say. The big deal is that now we're going to introduce depth. That's the only big deal. So although in the previous slide I said, oh, feed-forward networks only have length, but now CNNs will have both, not just the length, but width and height. Sorry, not just the length, but width and depth. The depth is a new part. The width is just a rearrangement of things will get you width. Okay, that's all I mean here. Yeah, so I'm gonna, so as I said, I mean, this is what I said in just now before getting to the slide, is that the new idea is that there's going to be a depth. So instead of just rearranging the neurons and saying, oh, I have a width and height, we actually want to create depth. And how are we going to create depth? And why does it help in parameter reduction? And why does it make sense for image data is what we're going to discuss next. Okay, so let's take a break for 10 minutes and then discuss that. Okay. Okay. Before we really get into like a deep dive on convolutional neural network, I wanted to show a couple of lightweight things so that we're not like bogged down by the details. Firstly, I think it makes sense to look at this PyTorch basics repository. So it's an old repository, so much of the code might not work, but it's an instructive one because it has some interesting basic explanation. At least part 1 makes a lot of sense. Okay, so it gives you a sense of what's happening with PyTorch and a little bit more familiarity with the basic data type there, which is a tensor. Okay, so I would suggest looking at this. In fact, I just opened the linear regression example by just clicking on open in collab, and like let's just run all. Okay. So you can see that very similar to NumPy, you import torch And there's a bunch of extra things that you import. I will not get into the details of what these specific imports are, but I wanted to show the problem, right? So sklearn has a sklearn, I guess scikit-learn has a nice helper function called make regression, which creates arbitrary regression problems. Okay, arbitrary regression problems. So you can say, okay, how many samples you need, how many features are going to be there, what's some noise level and some random starting point, and just create the x comma y data set for you. Okay, so it's just to create a synthetic data set so that you have something. So this is the data set. In fact, it's a very simple regression case. So it's just x versus y. You're just fitting you want to fit a line if you create this data set. Okay. So here in this notebook, and I will not go through the full details of this notebook. I'm just trying to show you that this is a very instructive notebook because it gives you a sense of gradient descent and everything else in the simplest setting, one-dimensional regression setting. Okay. And in your assignment also, you kind of do something like this. Not exactly this one-dimensional regression, but you do 1D regression. You do some regression problem with gradient descent. So here's the way so X and Y are just, so X and Y are, okay, let's see what X and Y is. Right, so it's just it became because we executed the whole thing, but it's 100 numbers and 100 numbers. Okay, y, x is one of the scalar value and y is one scalar value, and you saw the plot, right? So for example, x is between -3 to 2, and then y is between -150 to 150, right? So that's what x and y are. So first of all, we're converting them to tensors. Torch has the basic units are tensors instead of NumPy n-dimensional arrays. Okay. And there's some reshaping happening. This is for samples. Yeah, I don't know why there's a reshaping happening, but and there is a model defined. Okay, you will actually see this model maybe not in assignment 1, but you can do this in assignment 1 also. But there's some optionality to skip this stuff and directly get to something in assignment 1. But here's a linear regression model. Okay, what is it doing, right? It has so PyTorch lets you define directly layers. Okay, what are layers? In feed-forward neural network case, a layer was just a W comma B pair, right? So W and B together is like one feed-forward layer, right? One layer. So you can actually just define it like this, and not just PyTorch. TensorFlow and other packages also do the same. They just let you define layers nicely. So you can just say my layer is a linear layer. Okay. So you have one-dimensional data as input, one-dimensional data as output. What is your layer going to be? It's just going to be a coefficient, which is a slope, and an intercept. Okay, it's just two numbers, right? The W matrix is not going to be a matrix; it's just one number, and B is not going to be a vector; it's just going to be one number. Okay, so that's what this layer is, and there's some, this class definition may seem alien to you if you have not seen this before, but it's just a way to set up a neural network in PyTorch. Okay, you'll see this like hundreds of times if you in this course. So first time it may look alien, but it's just very, this is the pattern used. Okay, and then once you define that model with some, we want to learn the slope and the intercept basically, right? You can define the model. You can actually send it. So one of the ways you can send it to a GPU, PyTorch makes it, in PyTorch, you would do to the GPU. Okay, so you can do dot to the GPU to send that weights to the GPU if you want to use GPU. That's the way to do it. Well, that's not the important thing. And then you can define a loss function. Like, for example, there's a helper loss function called square loss already defined. So just like scikit-learn, right? So you can just choose many things by just giving default arguments and stuff. And this optimizer is exactly the stochastic gradient descent optimizer with a learning rate of 0.1. Okay, so it's just SGD on the model parameters. Model parameters of what? Just the slope and the intercept, two numbers, right? And then we are sending everything to the GPU. There's no GPU here, as far as I know. I don't know unless it says. Actually, we can. It's a CPU. Okay. And so now is the interesting part, right? So what we are doing here in this cell is kind of gives you a sense of this gradient descent that PyTorch is doing behind the scenes for you. Okay, so this cell is supposed to represent one step of your gradient descent. Okay, so I mean, this is just for visualization. We have model, we just put in training mode and we remove all gradients if there were any gradients from before, like just ignore them. And then for the given data, we do one forward pass to get predictions. Use the predictions with the ground truth to get the last value, right? I mean, this is something that you do everywhere. Once you get the last value, these are the two steps that let you compute the gradient at for every parameter of interest. In this case, there are only two parameters, slope and the intercept, and then take a step of the gradient descent procedure. Okay, those are the two magic lines. Here it's just linear regression, but even if you had a very complex model with like millions of parameters, as long as you can compute loss, do a forward pass to get to the loss, you just do loss dot backward. It will compute the gradients for you of the parameters of interest with loss with respect to parameters of interest. And once you have that, you can just do dot step to do one step of the gradient descent. Old values minus some learning rate times the gradient of the loss with respect to parameters would give you the new parameters, right? That's it. Those are two lines. And then it's just showing, okay, this remaining part is just for our understanding to see, oh, if you do one step of gradient descent, if the old parameters were something and new parameters were something, how better do the new parameters fit to our model? Okay, so you can see that because we only did one step, maybe the old parameters were such that the slope was like way off and intercept was way off. So if we just do one step, it moved a little bit, okay, which we don't know. I'm just saying that it moved a little bit. Now, all I'm saying is if we control enter, right, it'll keep moving. Okay, control enter, just do it like a few times. Can you see the slide change? Now it's becoming better and better. This is what gradient descent does, right? So it just makes minimizes the loss, right? So you have kind of getting to some loss value. Actually, yeah, MSE is 320 or something. I don't think you can reduce. Okay. You are reducing a little bit, but it doesn't. So that's what you would like in a for loop. For 100 steps of gradient descent or 1,000 steps of gradient descent, just do this. So that's what all PyTorch code and not just PyTorch, but like TransferFlow and other packages, that's what they help you do. They help you do these two magical things so that you don't have to worry about really thinking about gradients. But you might have to think about gradients because saturation effects and dead relus and whatnot. There is issues in the model specification that may be problematic and you may have to debug. But if you had a reasonable model, then these packages let you do a lot. Okay, so understanding this basic code, which because it's not doesn't have many other details, like it's not directly jumping to CIFAR10 and explaining what PyTorch does. So this is I would say a good example of something that you want to kind of spend some time on, because once you understand this elements here, then the next step of elements make much more sense. Like for example, here the data is being passed from GPU. If there was a GPU, okay, if the device was set at GPU, then this step .cpu sends the data from the GPU memory to your RAM of your of CPU RAM, regular RAM. Okay, and then .numpy converts that tensor to a numpy. So these are things that you will kind of slowly learn. So today, what I'm just showing you suddenly like something like this, but worth trying out this link, which is on the lecture 2 lecture goals page. Okay. And the second thing I wanted to mention, and we can probably see it again, is this repository called Netron. Actually, it's a nice repository which lets you visualize neural networks. Okay, so far we have not seen any complex networks, so maybe we are a little bit ahead here. But I mean, the app was written to kind of visualize any neural network. So even your neural networks, as long as you export an appropriate model definition file, you can visualize it here. Okay, so if you, especially if in assignment, maybe assignment 1 we don't do much, but in assignment 2 you would have a neural network, so you can always export it and see it. So here are some examples, right? There's a bunch of networks here that you can click on them, not click on them, like you can Google them and see what the networks are for. Like for example, so YOLO stands for you only look once, and it was a very popular architecture. It's still a very popular architecture for doing object detection, putting bounding boxes around images. Okay, it's a pretty complex model. We are not there yet. We are still working on CNNs. But if you wanted to look at it, oh, not that link itself, but if you click on the app, it'll kind of tell you what's okay. Given the input, there's a convolution layer happening, convolutional layer, which is what we're going to study now, is happening, and then some other layers which we have not talked about are going to happen. Leaky ReLU, so it's the leaky part of, instead of a ReLU, there's a little bit of extra wiggle room so that you actually still pass gradients on the negative side, right? And then some pooling operation, again a con, bash norm, leaky ReLU. So this is like a pretty good understanding of I mean, this visualization is not just by this app. I mean, you can also do it through directly through TensorFlow or PyTorch also, but I wanted to show you this link is also probably there. If not, I'll add it. Okay, any questions here? These two were just some lightweight information about PyTorch. Anyway, PyTorch you will kind of ramp up and you'll get used to it. But if you directly jump to a PyTorch code, which is like more complex, then it's going to be challenging. So you do something first, do the basics, get a feel for the tensors, linear regression perhaps, then you get to the bigger code base. Okay. If there are no questions, then let's come back to our CNN architecture. So where we stopped last time, just before the break, is we want to kind of see how we can add depth. Why does adding depth, why does adding depth make sense? We want to reduce parameters, we want to exploit some image properties. And that's kind of the two things. So how do you do that, right? So input has 32 cross 32 cross 3. Like we'll take the CIFAR 10 example. So 32 cross 32 cross 3. And output has a dimension of 10 classes, because the CIFAR 10 classes, airplanes versus birds or something else. So those 10 classes, you can have a degenerate dimension, right? You can have 1, 1, 10. So it's still a 3-dimensional tensor. Okay. So you can think of the input as a 3-dimensional tensor, the output is a 3-dimensional tensor. Although I added like two kind of useless dimensions, but input is a tensor, output is a tensor. So let's think of kind of processing a tensor to a tensor, right? So previously, if we had a 2 hidden layer network, it would be like this. What we can do is, let me say properly. Previously, if we had something like this, I know we showed the same picture with just 1 hidden layer, but this is the same idea on the with 2 hidden layers. All we did is like rearrange. Okay, what happens is each neuron still looks at everything before it, in the sense of we did before it in the sense of this was a vector, we just reshaped it into a box. Okay, this is vector, we just reshaped it like arrangement of numbers into matrix, basically vector dimension. But each neuron here still uses all the entries of the previous slice of bread, right? So that's what we're gonna kind of attack, okay, and do something there. So all we did is rearrangement here. Now what we're going to do, as I said, it's CNNs, is we're going to have an input tensor. We'll have depth, so 3 slices of bread in the beginning, right? Because the RGB channel, and then we have 10 scores. I mean, those scores, it's like 10 slices of bread, but the slices are like really small. Okay, and each layer is going to just transform from here. Each layer is going to go from a tensor to a tensor to a tensor to a tensor. Okay. So what does a tensor mean, right? It's just basically cells or numbers arranged in a way such that there is going to be depth, right? I mean, so again, as I said, if you think of input as like 3 slices of bread, where each slice is like a matrix, then every tensor is just a collection of those matrices. It's just it could have, let's say this tensor had like 5 matrices, one behind the other. That's one tensor. Here, 1, 2, 3, 4. Yeah, this also has 5. So 5 cross whatever. 3 cross 2, right? So that's it's like slices, 5 slices, one behind the other, right? So that's what we want to get to. Yeah. So I don't know if this is abrupt change, but I'm gonna still we will get to that neuron level perspective. Okay, that's what we'll see next. Okay, so far we are saying, okay, we can rearrange, we can have a depth, but I didn't say how we're going to have it. Before I'm going to specify that, I just wanted to mention that in a CNN, there's going to be the usual fully current layer that we have seen the first half of the lecture. There's going to be a new layer. That's what we're going to spend the next 15 minutes on. And there's going to be another small layer called a pooling layer. We'll discuss those two, the ones in the purple next. This one is nothing conceptually hard. It's just very simple, like, averaging of numbers or something. But I just want to briefly mention that if you knew these layers, the ones in the purple, which I'm going to discuss next, but if you knew them, then it's just exactly the same operation that we did with FIFA. It's just stacking them one after the other. So for example, you could have a input to a con layer. Okay, it's going to produce a tensor, and that's going to pass through, let's say, a pooling layer. It's going to produce a tensor. It's going to pass through a fully current layer. It's going to produce a tensor, but those tensors are like the fully current layer. We know what tensors are. They are just degenerate tensors. There's no extra dimension. Okay. So the input is like a tensor, 32 cross 32 cross 3. Let's say the con layer. We did say that there are neurons, like regular free forward neurons, but they can produce a tensor. Let's say this con layer produces a tensor which is 32 cross 32 cross 12. Okay, this is completely arbitrary. Nothing, it's just illustration. I'm just mentioning it. And then pooling layer, what it does is kind of averages numbers. Okay, so if there was a tensor which is 32 cross 32 cross 12, it's going to maintain the depth the same and just reduce the numbers. Instead of a 32 cross 32 slice, it's going to have, for example, a 16 cross 16 slice. So some compression on the width and height side, keeping the depth the same. Okay, that's what the pooling layer does. And we'll see actually more concretely what it is. And the fully current layer, let's say if it's a fully current layer, for it, the input being a tensor is like irrelevant. You can just vectorize this, as in like put it one below the other, like as he was saying, Lego block, and then maybe produce the 10 classes that you want. Okay? So going from a 69, 69, 12 to a 10 numbers. That's something we know. Wx plus b, basically. Okay. So what I'm trying to say is that you can think of tensors being passed around, and the only new things are these two. Whereas this is I already kind of briefly alluded to what it does. It's just averaging. So the only kind of unknown is the con layer. Okay. Some layers will have parameters. It turns out the pooling layer may or may not have parameters, and we'll see a version where there is no parameters. Okay. And optimization of everything is still the same gradient descent. With those things out of the way, let's now really focus on con layer, because that's where some magic is happening. So this layer, its input is a tensor, its output is a tensor, and this layer is going to be composed of what we're going to call a set of filters. Okay, a set of filters. Okay. What is a filter? And then we talk about then we can talk about the set. A filter is nothing but a linear function, okay, which is parameterized by a tensor. Okay, it's just a lot of words to say it's some sort of linear operation. Okay, it's parameterized by a bunch of parameters, and the parameters themselves are arranged like a tensor. Okay, that's all it means. Okay, so think of let's say parameters like let's say there are 27 parameters. They just arrange like a Rubik's cube, or basically 3 slices with a depth of 3 and a width of 3 and a height of 3. Okay, just 27 numbers arranged in a certain way. That's why I'm calling it a tensor. So each filter is just a collection of these 27 numbers. Okay, and maybe there are like 10 or 12 such filters. Okay, each filter, every time it operates on its input, it's going to produce one number. Okay, each filter is going to produce one number every time it operates on its input, and these parameters are going to be learned just exactly using backpropagation. Okay, each filter outputs a scalar to its input. So to output many numbers, you have to keep changing its inputs. That's kind of fine, right? So this filter, therefore, since we are saying it's represented by a parameter of tensor, parameterized by a tensor, it has width, height, and a filter depth. Okay, it has its own depth. Okay. In fact, this depth turns out to be the same depth as the input tensor. So if our first layer is a con layer, then the filter that is composed, that composes that con layer, in the sense that the con layer is a collection of such filters, those filters' depth should be the same as the input image depth. So if the input image is like a color image, then its depth is 3 because there are 3 channels. Then the filter will also have a filter depth of 3. Okay. If the first layer happens to be a con layer, let's say it is a con layer. In illustration also we said it's a con layer. Okay. Now to produce a lot of numbers, right? We need to produce even if you had like 12 filters, they're only going to produce 12 numbers if you just think of it as working with the input. So how does it work with the input? First of all, this is like a small Rubik's Cube. Okay, I don't know how many of you have heard of Rubik's Cube. Everybody's heard of Rubik's Cube? Okay, right? So our image is like, let's say 32 cross 32 cross 3, and this thing is like a Rubik's Cube. What we actually do is we're going to slide, which is the same thing as effectively what's called convolution. Okay, we're going to slide the filter across the width and height of the input image, okay, of the input volume. Okay, we're going to slide it. Okay, it's like we keep the Rubik's Cube at the top left, and we keep sliding it. I mean, at every step, we're going to do something. What is that something? We're going to convolve. Okay, we're going to use the filter weights or the filter parameters and that part of the input together to produce one number. And then we're going to slide. Okay, I mean, we're going to slide the filter, and there's going to be a new set of numbers. We're going to convolve, as in like basically multiply or just do something to produce one scalar quantity, and again with the same filter and the next part of the input region. Again convolve and again get one number. Okay? That's the key step. Okay. Once you get the number, we'll have to again do a nonlinear operation on that number. Okay, it's very similar to P4 neural network, just some sort of max of 0, x if you want. Okay, so let's actually look at a picture where let's drop the depth for a second, in the sense of, let's say our image was black and white. Okay. Although if there was depth, we'll talk about the depth in the next slide. Let's say our image was black and white. Then this is showing the green area. Actually, the whole thing is supposed to be green area. Let's say the green one is a input image. Okay, it has a bunch of numbers in it. Because there's no depth, the filter depth and the image depth, let's say, are 1 for now. Okay, let's say the filter is 3 cross 3 because the filter cannot have a depth different from the image depth, input depth. Okay, input tensor depth. So that's why it's just a 3 cross 3 cross 1, because the input is 5 cross 5 cross 1. Okay. Now, what does this convolve operation, sliding operation, I meant is that think of these red numbers as the filter parameters. Okay, they're fixed. I mean, for now, I mean, they need to be learned in training, but let's say in this illustration, they're fixed. All I'm doing is I'm putting this Rubik's Cube, it's kind of flattened, so therefore it's not a Rubik's Cube anymore, it's just a matrix. I'm just putting on this top left side of the matrix of the input and doing element-wise multiplication, and then spitting out a number. Okay, that's 4 for this this top, like these 3 and that one, right? I put the number 4. Then what I'm going to do is slide. Okay, go one step to the right, one step in terms of one column to the right. I'll have again 3 numbers on the input, potentially new numbers. Again, I'll multiply with my red numbers and produce a second number here. Okay. And then again slide one more, and that's kind of the edge. I've already got into the top right side. I'll produce a third number. Okay. I can't do move anymore. Now I'm going to go all the way back, do one step down, and look at this part of the input region. So each filter is basically what it's doing is look at parts of the input region and produce a number, and then you can also do a nonlinear operation on that scalar once you get a number. Okay. So is the operation clear? So in I don't know if this works. Okay, I can just open it. Forget EV/image kernels. So in black and white, this is what's happening. Okay, let me just go back here. Go here. Okay. So let's say, so since in the previous image we said let's ignore the depth. Depth will count to very quickly. This, can you see my cursor, the red area? So if you're on the top left, all I'm saying is the numbers here are the filter weights. Okay. For now, let's say they are fixed. I mean, we have to learn it through backprop. and intensity values, this is a black and white image, are these numbers, and we're just multiplying and adding them together, and I'm just putting that number there. Ignore the border for a second for now. The border is all blacks there. We're not really talking about this particular technology in detail. Okay, we're just talking about filter operation at this point. Don't worry about sharpen, kernel, and all that stuff. We're not at all related to that yet. Okay. And then we just do slide one step. We get different set of numbers, multiply element wise, slide one more step, slide one more step, and so on. That's how we are generating these numbers one at a time. Okay. Yeah.
How is it useful in terms of our model building? I mean, what is changing here?
What is changing here?
Because we're adding the layer to.
We are discussing a new layer called a con layer. It's a collection of filters, and each filter, how does it work with its input tensor? That's what we're discussing now. So this layer is going to be parameterized by these, let's say 10 or 12 filters. The filters have these some number of parameters. Okay, we're going to learn those parameters. Okay, but this operation, it's actually getting us something, which is that the number of parameters to learn is actually just the number of filters times the number of parameters per filter. Okay, it's not going to be a million weights per neuron. Actually, each filter, basically, think of each filter. So this is only one filter, right? So this is like fixed number. Let's say we are sliding this filter all over the place. This filter is producing a lot of outputs. Okay, each of the outputs you can think of as a neuron output. Okay, because there's going to be a nonlinear operation also applied in a second. But all these neurons are driven by the same filter weights, although they're looking at different input regions. Okay, so there's parameter sharing happening. This was not the case for feed-forward neural network, where feed-forward neural network, every neuron had its own set of weights working, dot producting with the input to produce an output, and then you do a nonlinear transformation. Right? Here, all these neurons, these are all neurons because they are all outputs of some. This is basically a dot product. Element-wise multiplication, whether you show it this way or whether you do a vector times vector, it's dot product. So all these neurons are producing output, but they're all parameterized by the same filter weights. Okay? So we have incurred a huge parameter reduction while producing so many neuronal outputs. Yeah.
So, like in this example, even in the slide, we are using one filter.
Yes.
We are.
I'm just showing illustration-wise one filter, but there can be 100 filters. You get to choose.
Okay. And each filter will have different values.
Each filter can have its own parameters. No, it doesn't have to be. Yeah, it doesn't necessarily have to have different values, but they all have their own parameters. You can tune them. Yeah.
And each filter, then we are going to is going into the non-linearity function after separately.
Yeah, each neuron, right? Once you produce a number, think of it as pre-activation. Once you have this number, all this non-linearity, at least so far what we've seen, is element-wise operation. So once you produce a number, just apply max of 0, that number, right? Or a sigmoid of that number, or a tangent of that number, right? That's what we're doing.
Is there any specific way we are deciding the parameters of the filter?
We get to choose the size and size of the filters, like depth, sorry, not the depth, but width and height. Depth we cannot choose. Depth is the same as the input depth.
Black and white picture.
For black and white, depth is 1. But for color, depth could be 3 if it is the first layer. But if the con layer happens to be the 5th layer, okay, its input tensor could have a depth of 50. Okay, that's fine. It's just that the filter for that con layer now has a fixed depth, it cannot have a different filter depth. That's all.
My question was like in this filter we have a set of parameters, like we are multiplying it with 0, 1, and -1 and 0.
Yeah, this is a predefined filter from signal processing that in this illustration, but we are not going to use predefined filters. We're going to learn the filter weights ourselves. So this filter is called a sharpened filter, and there are many filters in this. So this is pre-deep learning, and it's still useful today also. So the blur filter, left subbell filter, and so on. Okay, like actually one of them, sharpened filter, you can see that the image is sharpened on the right side, and if you use blur, it's like blur, right? Blurring is just averaging. Okay, that's why you see averaging numbers, right? So these are all constant numbers, kind of sum up to 1 type of a thing. Yeah. But those are predefined filters. This is just for illustrating the sliding process. Let's come back to our network. Okay, our filter discussion actually, because the next slide has a much more complex, not much more, but like a, not, where is the picture? I think I missed I'm skipping too many. Yeah. So sorry, I'll come back to the 10 slides before, but I just wanted to show you that if you had a depth of 3, let's say your con layer happens to be in the first layer, and you have an image which is of size 1, 2, 3, 4, 5, the blue areas, okay, 5 cross 5 cross 3. I mean, this by the way got cut. There's actually the same size as this guy. Then the filter, there are 2 filters being shown here in these two columns. This filter has depth of 3, and this filter also has a depth of 3. They're like Rubik's cubes now. Okay, and here we're just showing, oh, what if the second filter was operating on the input? What would happen? Okay. Now input already also has been modified. In the input, we added a boundary of zeros. Okay, that we will discuss in a second. But if whatever is the input, how is this filter, which now has a depth compared to my previous example, which did not have a depth? How are it going to work? Slide this matrix on the first slice, slide the second slice of the filter on the second slice of the input, slide the third slice onto the third slice of the
input depth. These 3.
Yeah, it just happens that the input depth is 3 because yeah, let's say we are at the beginning. The con layer is the first layer. That's why the depth is input is like a RGB channel, for example. Yeah. So you will do element-wise multiplication, element-wise multiplication, element-wise multiplication. Add all those numbers together and add the bias, and that's one number here. Okay. What is this? This is related to the first filter. Ignore it. So ignore the first filter, ignore the first box. You focus on this one. This one was generated by the second filter operating on the input tensor. Okay. The second filter has 3 filter depth is 3 because there's 3 slices in the input. Okay. Any confusion? I'll come back to, I'm going to explain this, maybe not through this example. And you can check the numbers later. Okay. they do work. Yeah. So filters are going to be small along width and height, generally, like 3 cross 3 example that we saw. And I also said that filter depth is the same as input tensor depth. So if the input is x times y times z, then the filter can also have the same z coordinate. Okay. And as we slide, top left to top right, and then one step below, we have to choose many things here. I'm going to slowly discuss them. We produce what is called a 2D activation map. It's a fancy name to say a matrix. Okay, we're going to produce a matrix. Okay. And these filters parameters will be learned during training, just like backdrop. Okay, those parameters are just learned through training. And what do these filters even do? I think in the illustration, the browser illustration said they are from signal processing, blurring, sharpening. Okay, so that's actually really feature engineering, to be honest. So the previous filters that we saw from signal processing with predefined weights, they're actually detecting edges, doing some operations. So these filters are actually supposed to learn or detect, not really learn, but like detect certain aspects, visual aspects of the image. Okay, if you're applying these filters at the first con layer. Okay, for example, we know that you can detect edges, you can detect colors, many things. Okay, so they're really just some sort of detectors of patterns. Okay, that's what these filters are. Okay, and that's why I can give you a piece of that. That's why these filters are sliding all over the place, because we don't know where the pattern occurs. Maybe there's a sudden pattern that's actually very relevant to predicting that to be like a cat and not a fox. Okay, where is that pattern happening? You need to know, and so that's why it's sliding. Okay. So before we look at patterns, we can as in the patterns, as in the outputs for some of these filter specific values, we can look at how the neurons themselves are arranged given this description. Okay, and basically just kind of I already mentioned that all these neurons are sharing the filter weight, so that's why there's a parameter reduction. I'm going to restate that. So what's happening really, right? So from a neuron perspective, neuron as in like the number that I produce and the output matrix, from the number perspective, I'm only looking at a small part of the input. right? Because top left produce one number. So top left small region produce one number. Okay. So it's as good as saying like the neuron looked at a local spatial region of the input tensor. Okay. This was not the case when we just rearranged the neurons when we went from fully free-fall layers to like we said we can just rearrange and get a height and a width. There, if you think of every neuron was looking at the entire input tensor, okay, just by rearrangement. And we're just, the reason why we're getting parameter reduction is because now each neuron is looking at a really small part of the input. Okay, that's called a receptive field. Okay, it's like looking at, it's like as if you have eyes and you're only looking at small parts of the input. Okay, and I mean, if your con layer is the beginning, then it's going to look at a small part of the, every neuron is going to look at a small part of the unit, its input. If the con layer is like the 10th layer, it's obviously going to also look at a small part of its input. But if you think of the original image, that neuron might be looking at the full image, okay? Because the 10th layer is looking at the small part of its input, but its input might have been generated from a bigger part of its input tensor, like whatever layer there was, maybe another con layer. So all I'm trying to say is, as you make the network deeper, those con layers filters or those neurons, all the immediate in terms of immediate tensor, they're only looking at a small region. But in terms of the ultimate input tensor, the input image, they may be looking at the full image. Okay, so they may be detecting complex patterns if they're that depth. Okay. Anyway, so in terms of, so once we understand that, right? So a neuron will be looking at. So think of this as like an output tensor. I put 5 neurons here, which means that there are 5 2D activation maps or 5 matrices, which means that there were 5 filters. Okay, 5 filters. Each filter produced the matrix, and we just stack them together. We got an output tensor. Okay. Yeah, I mean here just saying that if the filter is 3 cross 3 cross 3, the number of parameters is 27, and there's one bias parameter. Okay, and each neuron, these neurons, although they are from different filters, they are all looking at the same spot. Okay, the different filters as well, different weights, and therefore different numbers here. And then obviously you also do a nonlinear operation on each of those numbers. Okay. Yeah, all 5 neurons here are they're different filters, but they're all looking at the same spatial region. I think I have another picture. I think I missed it, but see, yeah. But in contrast, I'll come back in a couple of slides. But in contrast, all these neurons on the same layer, same matrix, they're all looking at different regions, but they're all using the same weights. I just wanted to contrast that. Okay. Actually, let me go linearly. So, as I said, size of output tensor depends on 3 numbers: layer depth, which is just so layer depth is the number of filters that you get to choose. Okay, I can choose 12 filters, I can choose 100 filters and whatnot. So whatever the number of filters, that's going to be the number of slices of my whatever 2D activation maps or matrices, and that's why how deep of a tensor I get at the output. Okay. Now in terms of width and height, that depends on a thing called stride and zero padding. Stride is how much do I move to the, like if I start from the top left, do I move 1 step or do I move 2 steps? Okay, if I move 2 steps, I'm probably going to get a smaller, in terms of like width and height, I'll get something smaller. Okay, so stride is that. And then zero padding is something which just to kind of ensure that you put zeros around each slice in the input side before you slide your tensor. In fact, in that black and white image, we had, I don't know if there was a zero padding. There was a padding?
Yeah.
Zeros? Okay. So it's just to kind of ensure that, if there's some pattern to be detected at the edge, you have some wiggle room to kind of cover that. But, why zeros? Why not put some other numbers? This is just a heuristic. Okay. So those are the things that determine the output tensor size. Depth, clear, number of filters, but width and height depend on these things. So for example, here, the reason we went from a 5 cross 5 matrix to a 3 cross 3 is because stride was 1 and there was no zero padding around. Okay. So if stride was 1, you can only do one step and you hit the right boundary. And so that's why you only have 3 columns here. Yeah, and here I just said, all these neurons are using the same filter weights, and in this green slice, one of the output matrices in this output tensor. And the key assumption is basically if a filter is useful for one region, it may be also useful for other regions. Okay, or put another way, there could be pattern that the filter, because it's sliding, can detect irrespective of where the pattern is. Okay. Okay, so yeah, I said all neurons in each step slice or each 2D activation map, they use the same weight and bias parameters. And that way you've really massively reduced the number of parameters. Okay, in fact, next slide mentions this. So the number of filters, let's say, is M. Okay, and then this layer therefore will have M times 28 numbers. Okay, this is way less. Let's say M is 100. 100 times 28 is just 2800 compared to something huge if you were using a feed-forward neural network. Okay. And there's some details about, okay, so this operation, it may seem weird, okay, we are doing something mechanical, we are sliding and stuff like that. At the end of the day, it's just a linear operation. Okay, you can write it literally as a Wx plus B, actually. But the W will have a lot of repeated entries. Okay, there will be a very structured way of writing the W. The numbers of W are not unrelated to each other, in the sense that they are related to each other. If you had a regular feed-forward neural network layer, Wx plus B, every row of W or every cell of W has nothing to do with other cells or entries of the W matrix. But here, the cells are related. Okay, that's all, mathematically is happening. Okay. And so since cells are related, there's going to be multiple incoming gradient pathways. And so there has to be some addition. And this is where I think there was a slide last time about if there were multiple incoming things, you just add those gradients up together, multiply with the local gradient and pass it back. Okay. I think, yeah. And so that was about parameter reduction. Here are some pictures from the actual the network from 2012, which did well, right? An ImageNet challenge. Here's the pictures from by just visualizing the filter weights at the first layer. Okay, it's a little bit of a deceptive picture because you can visualize filter weights at the first layer because the first layer's filters, their depth is 3, and so they look like images also because depth is 3 means you can plot them as images. So here, I mean, it may look like, okay, these are detecting edges and some gradients and so on, right? Why do you think the reason why I say that detecting things is because if is a part of the input which exactly matches this, then the numbers all nicely align, and so the numbers, it's like doing a vector product with itself, so it will have a high value. Okay, if there's a aberration, then it may have like numbers canceling each other and there'll be low value. So that's why I just meant that these are like some sort of low-level feature or gradient or edge detectors. Okay, it's a little bit of a deceptive one only because it's just, you will see similar patterns for many other CNNs. Okay, there's nothing unique that this particular CNN, just by looking at this, you cannot say that the CNN did something unique and interesting. Okay, but these are just the visuals that you can produce from AlexNet. We just talked about this. So okay, actually, let me talk about pooling next time. Let me not rush through the material. Any questions about the con layer so far? Okay, pooling layer is a simple topic, so I can just pick it up next time and just discuss that. Yeah, I mean, if you have time, just look at this. I don't think. Yeah, I mean, here you can go out, but if you go out, then there are no numbers here, and so they put some zeros at the outside. So this is a really nice page. Actually, this whole website is really good for various types of visualizations. Yeah, various types of visualizations, including least squares, principal component analysis, and so on. So it's very good to understand and ground your understanding of. And these are things related to machine learning, so certainly look into it. Yeah, we'll actually, so by the next lecture, actually, end of next lecture, you would know what a convolution layer is. We already kind of see what a convolution layer is. By end of next lecture, you will know what is batch norm also. And leaky is something that you will do in your assignment. So by next week, you would know what a leaky ReLU is. So and early next lecture we'll see what pooling is, and so max pool is. And so by then you should know what this network is doing, or at least how it's arranged. This is just Lego blocks, right? Once I said these layers are there, you just arrange in a certain way. There is some rules of thumb that follow to set up the network like this. In your second assignment, you'll see a popular network which won the 2015 ImageNet challenge called ResNet. And you'll see that has an interesting, it's same blocks, but some different wires. And you'll see what reasoning there is in the next couple of lectures. Okay, let's pause there. And if there are any questions, I can take it. Otherwise, let's break.
I have a question.
Yeah.
So I got like the note of convolution, as you said, one of the main assumptions is that, this filter that is either, we're either trading or creating is going to be useful in every part of the image.